here from previous. Okay, yeah, thank you. And thank you all for staying to the end. Yesterday's lecture, I emphasized the similarity between the emergent magnetic field and real magnetic field. And today, I want to go a little bit different direction. I'll show you that not everything is the same. In fact, there are new phases that seems to be only possible with emergent magnetic field in marine materials. And that is topological superconductivity. And this is something motivated by experiments by Zhengguang and by others. And also towards the end, I'll maybe briefly discuss how AI can help in quantum matter research. So the first part of this talk on topological chiral superconductivity was done with these brilliant postdocs, Ahmed and Daniel. They're both looking for faculty positions. If you have an opening, please interview them. And then the work on AI is initialized with this student at the UK in Cambridge University, E10, and our graduate student at MIT. And in fact, Tony's success got all my group members excited, and they all jumped into this AI area. Catch is a graduate student. Max and Filippo are two postdocs. So let me start reminding you the superconductivity. And the essence of superconductivity is that electrons form pairs, and these pairs of electrons all condense into the same state, or at least a macroscopic occupation of the state of electron pairs. And within the BCS theory, this all encapsulated by this simple manipulative wave function. It takes a form of a determinant, but it's not a determinant of individual electrons, but a determinant of every pair of electrons. And in conventional superconductors, the two electrons that form the pair have opposite spins. It's a spin singlet pairing. So once you have this macroscopic condensation, then you get the zero resistance because it's not individual electrons bumping away from disorder. In order to reverse the direction of electron, you have to really entirely change the macroscopic wave function of the Cooper pair, and that has a high energy barrier. And so colloquially, right? So a lot of people made an analogy that the Cooper pairing is like a marriage, and most of the superconductors we know are spin singlets. But as you just heard from Zhengguang's talk, right, that in rhombohedral graphene, right, there's something quite remarkable. That this electrons in graphene at low energy has this both spin and valid degree of freedom. It have isospin, and quite unexpectedly, that really fully isospin polarized electrons can still form pairs. Okay, and in this case, because the isospins are all identical, system is effective as spinless fermions, and then Pauli's exclusion principle necessarily implies if you exchange the two electrons coordinate, the pair wave function has to pick up a minus sign. Okay, so this means that immediately S wave pairing, D wave pairing, the even angular momentum pairing is forbidden. We are left with only P wave, F wave, these odd angular momentum channels. So this is something quite remarkable. There's something even more interesting associated with effective spinless superconductors, and that has to do with their topological nature. We know that when the pairing interaction is very strong, electrons can form basically charged 2e molecules, and these molecules can condense, and that's the so-called BEC regime, right? This is hard to achieve in electronic materials, but in cold atom systems, this has been routinely observed. Now, in this BEC regime, the system obviously has a large superconducting gap. There's a gap to break a Cooper pair. And on the other hand, in the weak pairing regime, the so-called Badin-Cooper-Schrieffer BCS regime, there's also a full pairing gap if you have a S-wave or P plus IP wave pairing. But what's remarkable, as pointed out by Reed and Green a long time ago, is that in the case of a spinless chiral P-wave pairing, the gapped BCS phase and also the gapped BEC phase are actually topologically distinct. Okay? One cannot smoothly go from one phase to the other as one increase the pairing interaction strength. And one way to see that is that if you look at the quasi-particle energy spectrum, it's determined by basically the energy measure the relative to chemical potential and the pairing gap, right? So then the BCS side, the chemical potential is above the bottom of the band. The delta is small, so states near the Fermi level sees a pairing gap, and the states away from Fermi level sees a single particle gap. On the other hand, in the BEC limit, the description within this mean field picture is that the chemical potential is below the bottom of the band. So in this case, the coherence length is very, very short, on the order of the size of the molecules. But as you sweep the chemical potential from above to below, right at the bottom of the band, the first term vanishes at k equals 0. The states at k equals 0 at the bottom of the band is right at the Fermi level. But when it's p-wave pairing, the p-wave order parameter is also forced to vanish at k equals 0. So therefore, what you get is a gapless state right at the transition between the PCS side and the BEC side. So this reminds us that the two gap spaces are necessarily separated by a gap closing phase transition, and that is the origin of a change of topology. There's a topological phase transition here. And because the BEC regime has a gap, has a large energy gap to single particle excitations, both in the bulk and at the boundary, the BEC side is non-topological. But on the BCS side, okay, even though in the bulk there is a BCS gap, on the boundary it actually hosts gapless Majorana fermions. These are the analog of the chiral edge states of the integer quantum Hall effect. But now these fermions are Bogoliubov quasi-particles. They are charge neutral, and this leads to a topological chiral superconducting state. Okay, and there's a lot of interest in finding Majoranas, and in one sentence, the key to Majorana is really to find the superconductivity of spinless fermions. Okay, and in the past, people like me thought a lot about how to coax electrons into a effectively spinless situation. But what Zhengguang showed is that in rhombohedral graphene, this all happens automatically. Now, I'll just very briefly mention our current understanding of his system. And as he mentioned, that in this rhombohedral graphene, the band bottom is quite flat, but also the band bottom is tunable by the displacement field. At a low displacement field, the band dispersion is monotonous, but as you increase the displacement field, you effectively develop some kind of maximum height of a dispersion, right? So if you look at the density and displacement field, the Fermi surface then changes from a small displacement field, you have a circular Fermi surface. As you increase the displacement field, you get an anomalous Fermi C. There's a bigger electron pocket and a smaller hole pocket. This is when you intersect this maximum height, and Fermi level intersects the maximum height. So we did a calculation using starting with repulsive Coulomb interaction, using basically the over screening due to the charge fluctuations, somewhat similar to the Latinger mechanism, and we found that the superconducting state has a chiral p-wave order parameter, and then based on this type of fermiology, it then follows that in the circular Fermi surface regime, the superconducting state is with chiral p-wave pairing is topological, similar to the Reed-Green conclusion. But when you have this annular Fermi surface, in this case, you have both a bigger and smaller pocket. In this case, the topological invariant actually is 0. Another way to think of this is that if your Fermi level is actually right here intersecting two pockets, as you further reduce the chemical potential towards the BEC regime, now the band bottom is no longer at k equals 0, but at finite k. And at finite k, the superconducting order parameter is actually non-zero. So this means that I can smoothly tune the chemical potential further below the bottom of the band without encountering a gap closing transition. This then means that the state in this annular region is topologically equivalent to the BEC regime and therefore non-topological. Yes?
With this, you need to see why one is B here, the other here.
Yeah, so this is exactly what I was trying to say. That, for example, if you are in this regime, when you have low displacement field, the band is monotonous, right? If you put a chemical potential here, this is when you have a circular Fermi surface. And if I now try to reduce the chemical potential to the bottom of the band to go into the BEC regime, the band bottom here is at k equals 0. So when Fermi energy sweeps to this point, the k equals 0 state is at the Fermi level, and also the p wave order parameter, because it's px plus I py, it vanishes at p equals 0. So for that reason, the k equals 0 point is gapless even in the presence of pairing, and that is the transition from the BCS to BEC. Does that make sense? While if the displacement field is 80 millielectron volt, if I park my Fermi level here, and again I can reduce the chemical potential towards the bottom of the band. But now at the bottom of the band, it's occurring at finite k. At finite k, this order parameter kx plus I ky is still finite. So this means that I can smoothly pass through this band bottom. So this means that the system you start with is already equivalent to the BEC regime. So that's the conclusion. Intent. Okay. Okay. So the what I'm going to mainly focus on is this after Zhengguang's experiment, a new system, twisted MOT2. It's a system that has been studied for the fractional quantum Hobbes effect, but this is a new experiment from Shanghai. Show that in the same device, actually the fractional anomalous Hall state at 2/3 filling coexists with superconductivity at a nearby filling factor. So this is a plot of Rxx and Rxy. This plateau here corresponds to the fractional anomalous Hall state at 2/3 filling. Rxy is quantized. Rxx has a deep minimum. But then here at the higher Hall filling factors, you see that both Rxx and Rxy vanishes. And that's what we expect for superconductor. And this is temperature dependence of the resistance as a function of magnetic field, and you see that there's a nothing transition. So this is something very unusual, right? In level systems, we never hear about superconductivity, right? So something interesting is going on. And in particular, let me, because there's a lot of interesting about perhaps superconductivity in the uniform magnetic field. Let me make some comment here. Now, in the presence of magnetic field, based on very general considerations, one can show that it's impossible to have a superconducting state that preserves translation symmetry. Okay, and the reason is that you take for example, a semiconductor two-dimensional electron gas in the presence of a magnetic field. This Hamiltonian satisfies the Galilean invariance. The kinetic energy is quadratic in momentum, as the electron-electron interaction only depends on relative particle distance. And in this case, actually, Kohn theorem forbids superconductivity. And let me go through this argument. If you take this type of Hamiltonian, you can rewrite it in terms of the center of mass momentum coordinate, as well as the remaining relative particle momentum and coordinates. The center of mass momentum and position are actually decoupled from all the other degrees of freedom, and in particular, it does not participate in interaction. So this means if you apply a uniform electric field, it only couples to, instead of thinking about a uniform electric field coupled to n electrons, it's better to think a uniform electric field only couples to a single degrees of freedom, that is the center of mass, position, and momentum. Okay? And the total current in this Galilean invariant system is directly proportional to total momentum. And from this, it follows that the center of mass degree of freedom, which experiences the electric field and experiences a magnetic field, it just undergoes a free cyclone motion, right? It just undergoes a free cyclone motion. And then it follows from that immediately that the Hall conductivity at the DC is quantized into some nu e squared of h. Nu is a filling factor, and sigma xx is 0. And in fact, it also follows from this that the entire conductivity as a function of frequency takes this general form. The absorptive part of conductivity, both in real part of sigma xx and imaginary part of sigma xy, it's a delta function at the cyclone frequency. So basically, optical absorption occurs only at the cyclone frequency, and that exhausts all the spectral weight. There's no spectral weight left at the DC. Okay, while in the superconductor, you expect the real part of sigma has a delta function peak at a 0 frequency. In the present magnetic field, if the system preserves translation symmetry, that's impossible. Now, you may wonder, what about hypothetically imagine some attractive interaction for electrons within the lambda level. And this problem actually has been considered. And if we put some fermions in the lambda level and turn on attractive interaction, of course fermions can pair. But the key point I want to make is that a pairing does not imply superconductivity. In fact, this beautiful work by Kun Yang, from many years ago, shows that if you take, for example, spin-full fermions in the lambda level and turn on attraction to pair them into bosons, these charge 2e bosons still feel the magnetic field. So instead of becoming a superconductor, these paired fermions become a bosonic quantum Hall states. And in fact, through this transition, the sigma xy, the Hall conductivity, is unchanged, as you expect from Galilean invariance. Galilean invariance dictates the Hall conductivity. One can also take spinless fermions and place them in the lowest level, and again, in this case, the system goes from a fermionic quantum Hall states into a bosonic quantum Hall states of pairs. No superconductivity. Now, I also mentioned that this Kohn theorem, the argument I just gave, it does not rely on strong magnetic field. One can ask, what about weak magnetic field? The whole argument still goes through. Now, we do know that superconductivity does appear in the weak magnetic field, but the superconducting state is known to be a non-uniform state. The superconducting order parameters develop vortices and an array of vortices. These are Aberystwyth vortex lattice. And in this case, constellation symmetry is spontaneous broken. And when this vortex lattice is pinged, for example, by some disorder, by sample boundary, and in this case, this co-Galilean invariant argument does not apply anymore, and here, true zero resistance state, the superconducting state, can be achieved. So there's nothing wrong with Kohn's theorem. Let me also briefly mention that this recent work with Leonid Glasman and his postdoc Daniel at Yale, we actually studied the topology of the superconducting state in this vortex lattice with magnetic field. So the idea is to take a two-dimensional electron system in the magnetic field, electrons field lambda levels, while superconducting order parameters form this Aberystwyth vortex lattice. So the question is, how does the quantum Hall states, in the absence of pairing, connect with this superconducting state with a vortex lattice? So the x-axis is Campbell potential. So these are a set of quantum Hall states. We assume the spin degeneracy. So the Chen number is always even integer from 0 to 4, 6, 8, 10, etc. And we turn on a pairing where the order parameter takes the form of Aberystwyth vortex lattice, and then you see that new phases appear. For example, there's a topologically trivial superconducting state in many parts of the phase diagram, but for example here, you start from, for example, the fourth lambda level, you turn on a pairing, you can actually get a true topological superconductor with a different Chen number. Okay, so now, yes?
Yeah, the thing that's in August, he goes down and the bank. I am confident.
Yeah, that's a good question. I mean, we haven't studied that. That's the spin polarized limit for this problem. Yeah, and I also want to mention that, this phase diagram is obtained from this really comprehensive calculation done by Daniel. It's very hard. I mean, I don't have intuition. It's one of the cases that it seems I have absolutely no intuition. Yeah. All right. So I think it's still an interesting problem. Yeah. Okay. So now let me come back to this twisted TMD. And as I mentioned last lecture, right? If you want to understand the essential electronic structure of these Moiré materials, of this type of Moiré materials, it's all captured by this particle in the periodic varying Zeeman field. And the idea is that the system has two layers. The two layers can be viewed as a pseudo-spin degree of freedom, and the interlayer tunneling acts as an off-diagonal component of the Zeeman field. It's a Zeeman field in the XY plane, while the potential bias behaves as the Zeeman field in the Z direction. And then by a local unitary transformation, one can basically rigorously derive a low-energy Hamiltonian. And in this low-energy Hamiltonian, the electron's layer pseudo-spin is locked. It's locked, but so effectively becomes spinless, but now pseudo-spinless. But now it acquires it sees an emergent magnetic field come from the bare phase. Okay. Now, this problem looks very similar to the problem of electrons in the magnetic field, in the Lambda level problem, but Galilean invariance is broken. It's broken because we have an underlying Morey lattice. So this the emergent magnetic field is not constant, but spatially periodically varying. And also, there's a periodic potential, right? So the breaking of Galilean invariance, it allows a richer set of phases. And that is a message I want to highlight, that the physics of interacting electrons in this emergent magnetic field could be even richer than a quantum Hall effect. Okay, and to explore this, we decided to take a very macroscopic approach. We want to solve a well-defined Hamiltonian and see what we get. It's like a numerical experiment, and we want to ask, is it possible to get, for example, superconductivity? So the model we choose for simplicity is again this type of models, but it turned out that when the periodic varying magnetic field is compensated by an appropriately chosen periodic potential, then this model actually gives you a exactly flat term band. And that was pointed out by Haram and Kasher a long time ago. So the idea is that when the magnetic field is spatially varying, the lambda level energy is also spatially varying with it. But if you compensate it with a periodic potential, then you can adjust it to make the completely flat again. Okay. So the details of what I'm talking about does not really depend too much on these details, as we'll show. But this is just convenient because the band is completely flat. The question is, in this completely flat band situation, what do we get? And also, we use a repulsive electron-electron interaction. Okay. So and also with this Morey materials in mind, as I mentioned yesterday, there was some questions during the discussion. In these twisted TMDs, the emergent flux is such that there's one flux quanta per Morey unit cell. And one flux quanta means H over E, right? For quantum Hall physics, the flux quanta is H over E. For superconductivity, the superconducting flux quanta is H over 2E. So please keep that in mind. Now, when the magnetic field is uniform, our externalization calculation shows a threefold degeneracy. That's exactly what you expect. Fractional quantum Hall effect. I should mention this is at fitting factor 2/3, again, motivated by the experiments. But then when we make the magnetic field periodically modulated, okay, sufficiently strong periodic modulation, clearly we see a different type of many-body energy spectrum. And here, what I plot is the momentum occupation number of the different block states in the Brillouin zone. And in the case of fractional quantum Hall states, all states in the lambda level has a uniform occupation. This is exactly what you expect. The fractional quantum Hall problem is completely non-perturbative, and there's no preferred single particle states. But here, when the periodic magnetic field is non-uniform, we see that what looks like a Fermi surface, right? It looks like a Fermi surface. And this itself actually is not new. There's a very nice work by Emil Bergerfos and his former student Ahmed, who is now a postdoc in my group. They pointed out that a flat band for electrons, actually, when you take into account of interaction effects, it could give rise to a dispersive band of holes. And this can be formulated in a completely rigorous way. You take a flat band of interacting electrons, because there's no kinetic energy for electron, purely through for interaction terms. One can perform a particle transformation and rewrite it in terms of the hole of it. And then, in terms of the holes, the kinetic energy appears, which is basically given by a self-energy from the interaction effects. In other words, if you have a complete field electron band, you remove one electron, then the change of the energy of the system depends on which K state you remove the electron from, right? And this self-energy basically depends, is determined by the flat band wave function. For a lambda level system, there's a high level of structure in these lambda level wave functions such that the self-energy is actually constant. But in a generic term band, for example, in the periodic varying magnetic field, even when the band is completely flat, this self-energy is K-dependent. And what this means is that in the language of holes, the holes acquire a dispersion purely from interaction. Okay, and this is why here I plot the hole dispersion. You see that the hole dispersion has a minimum at the gamma point. gamma point. It's very simple dispersion. Now, we actually already some years ago, right after the UW experiment on twisted MOT2, we actually noticed that there's something very interesting at the filling factor between 2/3 and 1, based on our exact dilation calculation. At the 2/3, we see that a fractional quantum non-pulse state and FCI. At filling factor 1, the band is completely filled. It's a quantum non-pulse effect. But in between, our many-body calculation again find a Fermi surface behavior. Okay, so this is actually very similar to what I just showed. That the interaction can actually induce a whole dispersion and can stabilize a metallic state at this range of filling factors. And because these bands has underlying barrier curvature, this metal is really a ferromagnetic metal. It should show a non-Hall effect, but it's not quantized. So we actually predicted this. And then recently, the experiment from Sheldon Shu's group, again, you see that RXY between filling factor 2/3 and filling factor 1, the RXY is strongly suppressed, and RXX now takes over. So this is what we expect for an unquantized anomalous Hall metal. And the recent experiment, right, again shows that in this range between 2/3 and 1, the RXY is finite almost throughout the entire region, except that in a small range of filling factors, it becomes superconductive. Okay, so in other words, superconductivity really develops within this anomalous Hall metal phase. And another support, I was just chatting with Oscar and decided to include this here. So this is again the Landau fan, right, of this twisted MOT2, and this is filling factor 1. And you see there's Landau fans coming from nuclear 1. This is exactly what we expect if you have a whole Fermi surface at the gamma point. It will give rise to a Landau quantization and this Landau spectrum. Yes?
In the previous slide, so the same results were just by the interaction.
Yeah.
On
right.
How much of this relies on a flat band? It just
this actually doesn't matter. So in fact, when we did this calculation for twisted MOT2, the bare electron has some dispersion, and the interaction actually further enhances it, so make it even more dispersive. Yeah, but the physics is really already the same. Yeah. Okay. Okay. So in fact, well, at some point when I talked about this anomalous Hall metal phase, and someone asked me, could this be a superconductor? Okay. At that point, I thought this was crazy. But now, after seeing the experiment, we decided to look at it again. And to diagnose superconductivity from excitation, we look at this quantity called the back pair binding energy. This is defined as the energy of adding 2 electrons minus 2 times the energy of adding 1 electron. So the idea is that if you have a pairing, then adding 2 electrons is energetically more favorable. And with this definition, pairing should be indicated by a negative binding energy. Now, in this flat band model, kinetic energy completely vanishes, and so the only energy scale is the bare interaction, repulsive interaction. Okay, in this case, we chose the short range repulsive interaction, which I call V1. This is exactly the same as the pseudo potential in quantum Hall systems. And now, to our surprise, that the pair binding energy is not only present, but it's actually very large. It can go up to about 20% of the repulsive interaction energy. Yes? It's a whole superconducting. Yeah, so I'll wait for 2 more slides. Yeah, it's a whole superconductor. That's the right way to think about it, is a whole superconductor. Okay, but the calculation, of course, is done for electrons to do the actual many-body calculation. So this is for a number of system sizes from 27 to 28, for example, and n is number of electrons. And you see that there's a negative pair binding energy, and with a period of 2, and that's exactly what we expect for pairing. And because the pair binding energy is so large, we find that the coherence length actually is comparable to interparticle distance, and this may be consistent with the observed very high quadriparticle field in twisted MOT2. Just for comparison, if conventional superconductors, the pair binding energy, the superconducting gap, is less than 0.1%. It's typically 10 to the minus 4 of the Coulomb energy. So it's a quite strong coupling superconductor. And let's further look at the superconducting order parameter. So this is again from exact dilation. We took the pair operator and computed its overlap between n and n plus 2 particle many ground states. And I plot this order parameter in band basis, and this is what shows here. You see that this order parameter is very large in around a circle near gamma point. That's exactly where the whole Fermi surface is. And the color represents the phase of the order parameter. It has a phase winding of 6 pi. So this is a chiral F-wave pairing. Recently, we also decided to look at this problem more microscopically. You take the order parameter from band basis, it combined with a single particle band wave function. Then we can reconstruct the order parameter in real space. And remember that the whole system fundamentally is a problem of particles in the periodic magnetic field with h/e flux quanta per unit cell. So what we expect then is that the superconducting state should be a vortex lattice. Right? So here, let me analyze, and here, this panel A shows the periodic magnetic field is highly non-uniform, right? And the pair wave function depends on 2 electron coordinates. So let me decompose it. Here I plot psi, the 2-particle pair wave function with the first electron coordinate fixed at this point. And I plot it as a function of relative distance between the 2 electrons. And here you can see it has 3 peaks, right? 3 peaks at these adjacent Mori unit cells. And if you further look at the phase winding of the relative electron coordinates, you see an F-wave pattern. Okay. Now, in order to see the vortex lattice, this is associated with the center of mass degree of freedom. I plot the pair wave function as a function of center of mass, after averaging over the relative coordinates. And here it's a bit hard to see, but what this illustrates is that there's an array of double vortices. So for example, if you look at here, the phase winds by 4 pi. And this double vortices is exactly what you expect associated with the h/e flux. Okay. Each emergent flux in the unit cell is h/e, and therefore the superconducting order parameter shows a double vortices. We have an array of double vortices that is locked to the Mori lattice. This is a chiral superconducting state in a emergent magnetic field. Now, to further probe the topological nature, we notice that if this picture is correct, that the superconductivity develops from the dispersion of the holes, and the hole is centered at the gamma point, then we expect that in the topological phase, the ground state should have an odd-even effect. Okay, the ground state should favor an odd number of holes. Okay, this is again counterintuitive because in a spin-singular superconductor, the ground state always prefer to have an even number of electrons. Every spin-up electron has a partner to pair with, the spin-down partner to pair with. But if you go to the spinless regime, and in the BCS, the weak pairing regime, the electrons, is all have the same spin, and you can only pair states between k and minus k. And for finite k states, there's no problem. Every k has a minus k partner, but the state at k equals 0 is a loner, right? K equals 0 has no partner to pair with. So that's why in the weak pairing phase, the ground state actually favors an odd number of particles. And in this case, it should favor an odd number of holes. And that's exactly what we find. Here I'm showing the total energy of the system as a function of electrons for system size with 27 and 28 unit cells. And in these 2 cases, you find that the energy is always lower when you have an odd number of holes. Okay, odd number of holes. For example, in the case of 27 sites, energy is lower at, 18 electrons, which is 9 holes. For 28 sites, energy is lower at 17, which again corresponds to 9 holes. So this is evidence that the superconducting state is topologically non-trivial. Okay, despite that the pairing strength is so strong, the coefficient length is so short, topologically it's equivalent to the weak pairing phase, and it arises from the emergent dispersion of holes. And because it's a F wave, it should lead to an odd number of chiral Majorana edge modes. Any questions at this point? Okay, so let me now start to summarize the first part of this talk and yesterday's talk. So basically, I've shown that in Mori materials, in particular, I'm focused on twisted TMDs. electron correlation and band topology together can give rise to many interesting phases, including fractional quantum Hall, chiral melting state, and there are many others I didn't get a chance to discuss. And I think it's a really exciting time. Also, there's exciting experimental developments every day. On the theory side, I think theories are useful in suggesting possible phases of matter, what could exist. This notion of fractional Hall effect without magnetic field, fractional train insulators has been around for quite some time. And also theory can even help identify material platforms, such as twisted TMDs. But also, as you can see, that to actually understand the system in detail, it relies a lot on many calculations, numerical calculations. And that's because we're dealing with a very strongly correlated system, especially when you have a flat band, right? And unlike the fractional quantum Hall effect, where you have a unified description of many different fractional quantum Hall liquids, for example, the composite fermion picture. And here, we see that there are many competing phases of complete different kinds, right? A 2/3 filling with a relatively uniform magnetic field, we get a fractional train insulator. But when the magnetic field becomes sufficient non-uniform, a totally different state, chiral method appears. And I didn't talk about it, but our current numerical evidence is that transition appears to be a first-order phase transition. So in this case, it's really difficult to achieve a quantitative understanding without accurate numerical methods. So this is the last part of my talk. So, and this is how I think AI can actually help us, okay? So, as we know that from AlphaGo to ChatGPT, last few years, AI has really changed many aspects of our society. And, the way, at least so far, I've been using AI in a very traditional way, okay? At least very traditional spirit. This is to basically use AI to generate a variational wave function, okay, for a quantum manipulated system. And the variational approach has long been used with leading to enormous success. So both the BCS wave function and Laughlin wave function are both, you can write them down basically in one line, right? In one line, okay? And that's why they are theoretically very elegant, and they capture the essential ingredients of the splitting phase of the fractional quantum Hall liquids. But also, these human-designed wave functions are also in some sense tailor-made, right? Tailor-made for each different phase, and it's generally not quantitatively accurate. So if you want to study competing phases in a strongly interacting system, can one find an unbiased way? Okay. So here I would argue that neural network has an advantage because deep neural networks are extremely expressive. They can potentially capture a wide class of wave functions, in a unified framework, right? And also, unlike many of the AI applications, here, we're just using the neural wave function to produce the trial wave function, and then it's optimized entirely through energy minimization. So once I have a wave function, I can compute the energy expecting value by Monte Carlo sampling, and then to optimize to lower the energy that through this backpropagation approach, this allows us to update the neural network parameters. So there's no external training data involved, okay? We just input the Hamiltonian. We just specify the architecture, how a neural trial wave function is produced. And there's no other human input. Okay, so we have been exploring this for several years now, and I can, to me, for continuum systems, this neural network VMC based on first quantized wave functions have achieved really unmatched accuracy. Okay. Many traditional methods, such as DMRG or tensor network, are developed for lattice models. But for continuum systems, really, I don't see any other alternatives. And my belief in this AI is sometimes inspired by this remark from Landau. He said, with 4 parameters, I can fit an elephant. With 5, I can make him wiggle his trunk. This is how traditionally, right, theorists have been very, very good at compression of the enormous amount of the data and distill the essential physics out of it using very few parameters. But of course, that's what you sacrifice is accuracy. On the other hand, there's large language models, the neural networks, they have billions to trillions of parameters, right? So, if you look at Landau's elephant, there's actually a paper that fit the lambda elephant using 4 complex parameters, 8 real parameters. And this is a ChatGPT image from, I don't know, a year ago. You can clearly see the difference. Okay. So now let me very briefly tell you some of our results. Before that, we have been using a single architecture, okay? And this architecture is based on the determinants, based on one or just a few, maybe up to 4 determinants. But these are not Saylor determinants. Saylor determinants are determinants built from single particle orbitals. Here, we use a generalized determinant that is built from many body orbitals. So each orbital depends on the coordinates of all particles, okay? And so what the determinant does, it guarantees this final wave function is antisymmetric. That's required by Fermi statistics. But other than that, other than this determinant structure, there's no Riemann input to it, okay? And how these determinants are generated, how these particular orbitals are generated, they're entirely through this straightforward neural network with weight and bias parameters, through this attention mechanism. And if you want to find out more, you can read our paper. It turned out without the attention, this architecture just reduces to stated determinant. Attention is a way to find correlations. It's exactly the same attention mechanism as used in ChatGPT. Okay, and this architecture was first used to study atoms and molecules by the DeepMind group, and we decided to give it a try to see how good it is on many-body quantum phases of matter. Yes.
This is almost determinants about the jastroid.
So we don't use jastroid. In most of the calculations I'm showing you, there's no additional jastroid at all. Yeah, you can put some extra jastroid, but that's not important for now. No real difference. Yes. Yeah.
You hold 10 minutes. One card that takes when you break the target for it.
Yeah.
You get the 0 be higher order.
I'll show you. Yeah, I'll show you. Yeah.
And they keep getting all things.
Yeah, the number of parameters, it ranges from, a few hundreds, tens of thousands to like a few million.
That's a number of them.
Oh, numbers, at most 4. Yeah. It's a very small number of determinants. We use, typically from 2 to 4 determinants. Okay, yeah, I'm going to skip this. And also, let me, again, sort of emphasize the philosophy that our philosophy, we want to basically input as little information about the system as possible. So other than this determinant architecture that uses determinants, there's no additional human input at all. And the weights and bias are randomly initialized, so it doesn't know anything really about the system at all. And we just want the optimization to take us wherever it finds. And this is really exploring mode. It's like a numerical experiment. So, as the first example test that we look at 2D electron gas in the pure potential. This is describes some TMD heterostructures. And what I'm showing here is that depending on the interaction strength, at the 2/3 filling, you can either be in a Fermi liquid state where the ground state charge density has the same periodicity as the Maury lattice. As you increase interaction, you can transition into a generalized Wigner crystal where the charge density is spontaneously enlarged in your cell with a square root 3 by square root 3 pattern. You can also look at density correlations. In the Fermi liquid side, it's what you expect for liquid, but in the Wigner crystal state, you see these correlations, strong correlations of a crystal. Again, the same neural network, finds both phases at different interaction strength. Okay. Now, what really got me interested is this work Tony did. We studied the problem of the fractional quantum Hall effect, and we use a geometry that's first introduced by Kun Yang. Okay, and is with electrons that live in a two-dimensional plane, and there's a positive charge neutralizing background disk at some distance d away from it, and this confines electrons into a well-defined area, and we apply a magnetic field, and we look at the different filling factors. So here, I'm solving directly the many-body Schrodinger equation without any lambda level projection or any lambda level truncation. the neural network does not know such a thing as lambda level. It just sees a many electron Schrodinger equation. That's what it wants to compute the energy and minimize it. Okay. Now for various number of electrons, we compare the neural energy with lambda level projected excitation, and in this case, the so-called ED is no longer exact because we neglected the lambda level mixing. So excitation actually, in this case, gives you upper bound to the true ground state energy. So when the lambda level mixing is weak, we find that the neural network energy and the ED energy is very close, but neural network energy is still lower. Okay, so basically this determined based neural network already outperforms lambda level projected ED. And one can further look at the ground state charge density, and this is for 12 electrons. It has this is for Coulomb interaction, and you see that the charge is not completely uniform, but this is exactly what you expect for a disk geometry. But the important thing is that we evaluate the angular momentum of the system, and at 1/3 filling for 12 electrons, after optimization, after convergence, the angular momentum is very precisely quantized into 198. That's exactly expected for the Laughlin wave function. And Oscar, this is about a question. If I fix the n-1 particle coordinates and plot the many-body wave function from the neural network as a function of last particle coordinates, and this is the Laughlin wave function. The Laughlin wave function has only third-order zeros, but if you look at the true Coulomb ground state with lambda level mixing, every third-order zero splits into 3 first-order zeros. And that's actually what you expect on physical grounds, because at a very short distance, the Coulomb repulsive energy blows up. It's far larger than any cyclone energy. So at a very short distance, the ground state wave function should have only first-order zeros, and that's what we see. Okay. Later I'll show you, if you're interested, I'll show you that if we want to reproduce the Laughlin wave function, we can. Instead of minimizing energy, we can maximize the overlap with Laughlin wave function, and in that case, the neural network reproduces beautifully third-order zeros. Let me just be quick in saying that if I turn on strong interaction, when lambda level mixing very strong, we actually get a different state. For example, this system now has a different quantized angular momentum, and this may be a finite size version of a Wigner crystal. And also we can compare the energy from neural network and from excitation as a function of interaction strength, lambda level mixing parameter lambda. And you see that at the strong mixing, the neural net energy significantly beats lambda level projected ED. So again, determinant-based neural network, right? It actually can discover fractional quantum Hall states, discover potentially Wigner crystal states entirely through manipulation without any pre-knowledge. We know the Laughlin wave function. You never write it in the determinant form, right? Typically you don't do that, and with no input, but it still works. Okay, and I can briefly mention one thing that's recent discovery by the neural network. Our motivation is to study this potentially non-abelian quantum Hall states in a wide quantum well that's discovered by Mansour Sharagan, and there's a long history of study of the bilayer or wide quantum wells, Greg and Jim Eisenstein, and most of the theoretical studies, right, of the quantum Hall problem is started directly with 2D electron gas, but in this wide quantum well, the thickness matters. So we decided to start directly with the 3D electrons confined by quantum well potential with neutralizing background charges and with Coulomb interaction, and see what do we get. Okay. In the interest of time, I'll just briefly tell you some of the results. So there's two parameters in this problem. One is the interparticle distance, the RS. The other is the layer quantum well thickness in units of the Bohr radius. And for these parameters, we find that the charge density in a thin quantum well is peaked at the middle, and this is exactly what you expect for a single subband in the z direction. But for wider quantum wells, you find that the charge density is split into two peaks. So even though it's a single continuous quantum well, the Coulomb interaction drives the formation of a double well. Okay, and here what I'm plotting is the momentum occupation number of the first and second subband. In the monolinear regime, only the lowest subband is occupied with a big Fermi surface. In the emergent bilayer regime, both lowest and the second subband there's a Fermi surface with different size. Now, these are all what you expect, but when we go to even strong interaction regime, meaning that if I reduce the charge density, go to larger RS, this is a regime that DFT method cannot work at all. And this is a regime where you expect some kind of an electron crystal, right? In the monolayer regime, we get a clear Wigner crystals, but interesting thing, in the bilayer regime, we find all kinds of unexpected crystals. Here, this is the total charge density, and I decompose into 2 layers. For example, here is a relatively small layer distance, emergent layer distance, or the quantum well thickness. We see that you get 2 square lattices on each layer, and they are offset from each other to minimize the positive interaction energy. For different thickness, we find that on each layer, you have a triangle lattice. They are laterally offset, but they're rotationally aligned. So together, they form a honeycomb lattice. The dark spot means high electron density, okay? But most interesting and a complete surprise to us is that at some other parameter regime, we find that on each layer, electrons form a triangle lattice within a crystal, but the 2 layers are spontaneously 30-degree rotated away from each other. With this 30-degree misalignment, we don't have a crystal. We actually have a quasi-crystal with 12 bright peaks. Okay, so this is a discovery by AI of electron quasi-crystal. Okay, we will still try to understand this what better. Okay, so just the last slide. How much time do I have?
Very good.
And the end. Oh, okay, that's perfect. Yeah, let's just one last slide. Okay, so after all these numerical experiments, it got me really intrigued. So why is it that the determined architecture, for example, is so powerful? Okay, and for a lot of the machine learning applications, there is some underlying rigorous mathematical theorem. In particular, the universal approximation theorem says that a feed-forward neural network called a multi-layer perceptron can actually approximate any continuous function over a compact domain to arbitrary accuracy, meaning that if you are willing to increase the network size sufficiently, they can improve the accuracy to arbitrary precision, okay? Now, for us, when we deal with particles, quantum particles, we're not dealing with generic functions, but the wave function has to satisfy the statistics. So for bosons, the wave function has to be symmetric. Fermions has to be antisymmetric on their particle exchange. Now, talking to ChatGPT, I learned that for continuous symmetric functions, there's a thing called deep set. Okay, so something work from Google DeepMind, synthesized many previous ideas. They showed basically that there is also a universal approximation theorem for continuous symmetric functions, meaning that there's a way to use neural network to generate a wave function that are guaranteed to be symmetric. And also any symmetric wave function can be approximated to arbitrary precision, but if the network size is sufficiently large. Okay, so you cannot directly use MLP anymore. You have to make some modification to it to ensure the permutation symmetry. So then the question is, what about for fermion wave functions? For antisymmetric functions, is there a universal approximation? And these 2 papers I wrote, this is trying to address this issue. So let me just give you the final result. I'll be happy to discuss during the questioning or over lunch. So for any continuous antisymmetric function of n-particle coordinates, one can actually rewrite it in the exact way as follows. You define a lifted function. The lifted function depends on n-particle coordinates and a few extra coordinates. It's like an extra dimension. And then I call these eta. Okay, these extra variables I call eta. The wave function is recovered when the eta is set to be some function of the previous previous arguments of the particle coordinates. Okay. Now in this construction, psi needs to be symmetric in particle coordinates r, but odd in eta, and eta is antisymmetric in particle coordinates. This then guarantees if I permute any 2 particle coordinates, okay, this first part of the of the variable is symmetric, does not change psi, but then eta changes sign, and because lifted function is all in eta, it changes sign. So in other words, this constraint guarantees that if I can find such a lifted function, it guarantees to give me antisymmetric wave functions. But also, this representation is universal in the sense that one can show that any continuous antisymmetric function can be exactly rewritten this way. There exists eta and psi, okay, that do the job. More importantly, this eta function can be very simple, okay, can be very simple. In fact, this more recent work showed explicitly that I can just take this eta to be a stated determinant, or a few stated determinants, single particle stated determinants, and then the rest of the lift function can be written in terms of symmetric functions of particle coordinates, multiply this stated determinant and summed over the number of determinants. Okay. Now, the remarkable thing is that for two-dimensional systems, okay, on the compact domain, only two complex value state determinants are sufficient to represent any antisymmetric function. Okay, and for the details, you can read in this paper, but the basic idea is that there exists this determinants. These are, in fact, these state determinants. If you choose the determinants to be the quantum Hall wave function, okay, quantum Hall wave function. The quantum Hall wave function has a very interesting property that it only has zeros when particles coincide. This is not shared by any generic wave function. If you take a non-interacting metal or interacting metal, it doesn't matter. The wave function has many more zeros than collision zeros. But the integer quantum Hall wave function and Laughlin wave functions has this unique property that it's only a zero when two particles coincide, but not elsewhere. And because of this property, and we know that the integer quantum Hall wave function can be written as a van der Waals, can be written as a determinant. So for that reason, you can show that the two determinants is sufficient for 2D systems. Okay, and my best result for higher dimensions so far is that you need of order n determinants. And maybe in the future this can be improved. I don't know. This is a question. I think it's a really interesting question. Yes? Yeah, so with some caveat, graphene could also work. Yeah, with some caveat, graphene can work. So, okay, so what this says then, the previously, right, what I showed you is that the neural network we have been playing with, experimenting with, is based on generalized determinant, and it was unknown whether they are universal or not. Here, I show you that this architecture with just two determinants is universal in 2 dimensions, and you can actually absorb this symmetric factor into one of these single particle orbitals, and then it becomes one of the generalized orbital. So this then, it follows that for 2D systems, a generalized determinant with 2 complex valued orbitals is also sufficient. So with this, stop. Thank you for attention.